This is nuclear physics introductory course, and it is for both undergraduates and graduate students. Today, we will talk about the fission reactions and few ideas about the neutron and their properties. I am Dr. Nasir Mirza, and today we will cover the neutrons, the properties of the neutrons, and the fission reaction in general, in detail. So here we go. Neutrons were discovered originally by James Chadwick in 1932. In 1920, Rutherford had already postulated that there were neutral masses in the nucleus of atom, and atom is not really the protons, it is not really the electrons only, but a combination, a nucleus which contains protons and something else as a neutral massive particle. James Chadwick bombarded beryllium target with alpha particles. The alpha particle source was available, and he produced neutrons as a result of this bombardment in a paraffin block. The paraffin block had rich protons or the hydrogen atoms, and therefore the neutrons knocked down the protons in the paraffin wax, and measurements of the protons emerging from the paraffin were really a signature of the neutron presence, and it was said that the neutron mass is comparable to that of the protons. This is the original detection and the instrumentation that was done by James Chadwick. If we go further into the discovery of the neutrons were allowed to collide with protons, and the protons were in turn detected, and their energetics was measured. And with the help of Geiger counter, they were counted, and it was shown that the neutron's mass is comparable to the mass of the proton. Here is the schematics. If you look at the schematics, we have a polonium source placed within a shielded system, and a beryllium is placed in front of it. Then supposedly the alpha particles are striking the beryllium and the neutrons are getting out. These blue colored particles are going in the direction of paraffin. So they are now hitting the paraffin, hydrogen atoms in paraffin, and from hydrogen atom, the protons are getting knocked out, or the collision is taking place between the neutrons and the protons, and basically protons are coming out. Then the ionizing chamber is placed in front of it, or some Geiger detector is placed in front of it, and the current is measured, or the counting is done. Then basic properties were detected, like rest mass is 39.55 million electron volts per C square is the mass, and it is a little bit more as compared to the mass of the proton. The neutrons have the electric charge 0. Their mean life is about 14.76 minutes in free atmosphere. They have a spin half. So a neutron cannot survive unattendedly in nature. Once it is free to move around, it will decay. It will break into a proton and electron and an antiparticle, and its mean life is about 14.76 minutes. Let's talk about the properties. The mass originally figured out, and in terms of the million electron volts per C square, it is 939. It has a spin half. It is a fermion, and it obeys the fermionic statistics. Neutrons have no net electric charge. Neutrons have no they have non-zero magnetic moment. The free neutron outside nucleus are highly unstable. They will decay through the weak interaction. Mean life of the free neutron is about 882 seconds. Natural neutron background of free neutrons exists everywhere. Neutrons cannot directly cause ionization. Neutrons ionize matter only indirectly. Neutrons can travel hundreds of feet in air without any interaction. But in water, they cannot travel more than 30 centimeters. So water is a very good shielding material for any type of neutrons. The small neutron sources, if we would like to talk about the sources, the radioactive sources that can undergo the spontaneous fission. Certain isotopes that are now known to us that do the spontaneous fission and emission of neutron happens. Most commonly used spontaneous fission source is radioactive isotope californium-252. It is a spontaneous neutron emitter. Typical californium-252 neutron source emits 1.10 to the power 7 to 10 to the power 9 neutrons per second. A very costly, very expensive, and a rare source of neutrons. It has a half-life of 2.6 years. Another type of neutron source is the americium beryllium neutron source. Such neutron sources are really byproduct in which the alpha particle hitting beryllium. This is the original method to figure out the neutrons, and James Chadwick had used this, and this is one of the sources. The polonium beryllium source or the americium beryllium source, the alpha emitters combined with the beryllium give the neutron source. Americium emits alpha particles. Alpha particles are absorbed by beryllium and compound nucleus is formed, and then it becomes the carbon, and a neutron is emitted, and the energy is taken by both of these, but the large amount of energy is taken by the neutron. The source strength of these sources is measured by the alpha source. So the larger the alpha source, the larger will be the strength. For example, 1 curie americium beryllium source means that it has 1 curie of americium-241. Let's now talk about the nuclear reactions. Nuclear reactions became possible after the discovery of the neutrons because neutrons had no hindrance in going to the nucleus. Protons were really repelled by the positive charge of the nucleus. However, the neutrons are not repelled by the positive charge of the nucleus. They can directly interact. So a compound nucleus theory was formed that a nuclear reaction is a two-staged process. It is composed of formation of a relatively long-lived intermediate nucleus and a subsequent decay. The incident particle loses all of its energy to the target and becomes an integral part of the nucleus, the unstable nucleus. And this is called a compound nucleus. So here we show by a star. If we look at this reaction, the compound nucleus then further disintegrates into a small particle B and a product nucleus Y. So a nucleus which is hit by incident particle, it is absorbed in it, converted into a compound, and then compound is broken into a nucleus and a small particle. The Z star is a compound nucleus, and the formation of this compound nucleus will guarantee the production of the other types of the nuclei. So this was really the artificial radioactivity or the nuclear birth of the nuclear reaction. Rutherford went on doing many such experiments. James Chadwick had already produced the neutrons, and these were really subsequently used. If we look into the nuclear reactions, we find that nuclear reactions do conserve the mass number Nuclear reaction demands that the sum of the reactants mass number must be same as the sum of the product mass numbers. Similarly, the conservation of atomic number must happen. It means that the sum of the reactants total charge must be same as the sum of the product's total charge. So charge cannot go anywhere in the nuclear reaction. Conservation of energy must take place. It demands that the total energy of the reactants must be equal to the total energy of the product. The total energy is the sum of the rest mass energy and the kinetic energy of the nuclei. The conservation of linear momentum must also remain conserved. We demand that total vector sum of the reactants' linear momentum must be equal or same as that of the products. Conservation of angular momentum. The demand is that the total vector sum of the reactant's angular momentum or the spin must remain same as that of the product. And then the conservation of isospin. The total vector sum of the reactant's angular momentum and it should remain same as that of the product. These are the conservations that are really needed in the nuclear reactions, and nuclear reactions then can be developed, can be predicted, can be simulated. Various types of the neutron Z reactions are there. The neutron reactions, the first one is the elastic scattering. Elastic scattering occurs when no energy transfer is taking place between the target nucleus and the incident particle, only the direction changes. For example, a lead nucleus is hit by a neutron, and neutron gets scattered through it, and it is a scattered neutron coming out, and the lead is going in the other direction. In this, all the conservations are happening, and the transfer of energy in terms of the kinetic energy is not taking place. Only the direction in terms of the momentum is conserved. Inelastic scattering is a type of scattering when the energy is transferred to the product. The difference of the kinetic energies is saved in the excited nucleus. For example, Ca40 has an incident neutron, and the emerging neutron has a different energy, shown here as N prime, and Ca star is the product nucleus, which is going some other direction with some other kinetic energy. The capture reactions. Both charged and the neutral particles can be captured by nuclei. And this is accompanied by the emission of gamma rays. For example, neutron capture produces a radioactive nuclide. Here is the example. U-38 is absorbing a neutron, is capturing a neutron, and getting converted into uranium-239 and a gamma. In its excited state, it emits and becomes stable U-239. So a capture reaction has a gamma emission, and sometimes it is termed as a radioactive capture or radiative capture. The transfer reactions. These reactions are where the absorption of particle is accompanied by the emission of one or more particles. That is the transfer reaction. For example, a neutron is absorbed in a nucleus and a proton is emitted, or a neutron is absorbed and an alpha particle is emitted, or a neutron is absorbed or a deuteron is emitted. Such a reaction is a transfer reaction. Or a neutron is absorbed and the two neutrons are emitted. Let's talk about the fission reaction, which is part of the neutron reactions. Nuclear fission is a process in which the nuclear reaction occurs with the nuclei, and nucleus splits into smaller parts, the latter nuclei. For example, uranium-235 absorbs a slow neutron, becomes U-36, and then it is separated into two parts. They are called fission products. And 2 to 3 neutrons are also coming out with it. So basically, 3 things or 4 things are happening. Fission products are coming out as fragments, and 2 to 3 neutrons are also coming out as a result of the fission reaction. So a fission reaction is a complicated reaction in which the atom splits, the nucleus splits. The compound nucleus does not really keeps its shape. It breaks into 2 parts and also gives off the tiny little ones, the neutral ones, the neutrons, to come out. Let's briefly talk about the possibilities and the probability of the reaction, which is indirectly termed as the nuclear cross-section. Let us consider a beam of particles which is incident on a thin sheet of material, which is containing n nuclei per unit volume, and the thickness is x. The area on which the beam is hitting is A. If the particle interacts only with the dx or dn number of the particles that are thought to be removed from the beam, and they are passed through the slab of thickness dx, then we can say that the cross-section, the nuclear cross-section, is the effective area of the nucleus for this particular reaction. Then the total number of the nuclei that are present in the path are the number of n nuclei per unit volume multiplied by the dx distance, which is a thickness distance, and A is the cross-section area which of the beam which is removed. So dx into A is basically a volume, and multiplied by the number of the nuclei that were there, number of nuclei per centimeter cube, we get the number of particles that are present within this volume. The effective area available for the reaction is then, if you multiply this whole thing with the cross-section in centimeter squares. Now we talk about the dn over n, which is the interacting particles per incident particles, or the effective area of the reaction divided by the target area. So both are same. Therefore, this term n multiplied by dx multiplied by A into sigma divided by the total incident area, A, the target area, which is equal to n times the cross-section multiplied by dx. And this is basically the rate of change of n with respect to n. So rate of change of n with respect to n is the number density multiplied by the dx length and the nuclear cross-section. Since they are being removed, so the term negative is used in the expression. So the cross-section. Let's see a bit mathematics. Dn over n equal to minus n times sigma times dx. And if you integrate from n naught to n, from 0 to x thickness, we get at this result that the number of atoms after the distance x will be equal to the original number multiplied by e to the power minus n sigma x. So the exponential decay, exponential change is occurring as the function of the distance. The beam is getting removed as you progress in the thickness x, and the sigma is the cross-section. It is the number of the surviving particles, which decreases exponentially with the slab thickness, and the unit of the nuclear cross-sections is expressed in meter square or centimeter square. And these units are huge. Generally, these are expressed in terms of barns for the atoms or nucleus. The 1 barn is equal to 10 to the power minus 28 meters square, or 10 to the power minus 24 centimeters square. So cross-sections are also telling us about the probability of reaction, probability of interaction per unit nucleus per nucleus in terms of the area imposed or shown, and it is the area shown by the nucleus for the particular reaction. Larger the sigma, the cross section, the larger is the probability of interaction. The capital sigma is called the macroscopic cross section, and it is the number of atoms in the material multiplied by the microscopic cross section, and it is of a unit 1 over length, because number density is number of particles or the number of atoms, the number of nuclei per centimeter cube, and cross section has the units of centimeter square. Therefore, sigma, the macroscopic cross section, has unit of 1 over length, 1 over centimeter, or lambda is the mean free path, and it is 1 over sigma. It is the mean distance traveled by the particle without any interaction. From one interaction to another interaction, the average distance traveled is lambda, which is 1 over macroscopic cross section. We will talk more about the cross section in coming lectures. Let's briefly discuss the induced fission and its link with the liquid drop model. We have already seen the liquid drop model, in which the nucleus is assumed to be a liquid drop-like thing, in which there is a balance of forces. One force is the attractive one, which keeps on compelling the nucleons to be in the bound form within certain confinement, or spherical confinement. The other is the repulsive force, which keeps on asking for the repulsion that asks for moving away. So the difference or the balance keeps the shape of the nucleus. This is U-235, already a big nucleus, and when it is hit by a slow neutron, this creates instability and a deformation or excited state or a strong oscillation. One moving like this in an ellipsoid form, and then in another orientation, ellipsoid form. So it keeps on shaping in different directions until it starts breaking into two parts. And the electric repulsion becomes large enough that these two fragments are formed, and they form a neck. This neck becomes smaller and smaller, and eventually they break into fission fragments. And some of the neutrons, the neutral particles, they become independent and free enough to move away, but they carry energy, and their energy is of the order of 10 of million electron volt. And the fission fragments also have a very high kinetic energy, and they move apart. So that is the liquid drop model, in which the liquid fails to keep the drop in its shape. In a fission reaction, the release of about 200 or more than 200 million electron volts per atom occurs. And 2 to 3 fast neutrons also appear. They are fast neutrons, which means their energy is of the order of million of electron volt. 1 to 10 million electron volt is the energy range in which they come out and move, and therefore they are termed as fast. Let's calculate the fission reaction's Q value and find out the energy released in the reaction. The energy is basically the mass of particle A, mass of the particle X before the reaction, and the mass of the particle after reaction Y, the mass of particle B after the reaction. In this particular case, if we choose this kind of a reaction to take place, in which a neutron is absorbed by U-235, and rubidium and cesium are the two fission fragments, and also one neutron is emitted, then this is one complete nuclear reaction. We would like to find out the Q value. The solution is we go further to find the total energy released with the help of the mass change in the mass. The mass of U-235 minus the mass of the rubidium minus the mass of the cesium minus the mass of the neutron will give us the total energy released. We have not included, I'm sorry to put the 2 neutrons here, and that is why the 1 neutron is shown here. More than 1 neutrons are released here, and therefore we were not able to show that. But in this particular case, we see the 2 neutrons and the 1 neutron originally. So the net 1 neutron mass is there. So from the table of masses of isotopes, U-235 is 235.04. Rubidium 92.9, cesium 140.9, mass of neutron 1.00866. And if you subtract, you get the net balance as a delta M equal to 0.21843 atomic mass units multiplied by 931.5 million electron volt of energy per atomic mass unit. So it is about 203 million electron volts. People say that this energy ranges from 200 to 210 million electron volts for different types of the products that are produced. Because it is not fixed that the rubidium and cesium will be only things that will come out. These masses can change, and the fission fragments of different types, but there's some of the mass number will remain same, 236. But these numbers can change, and these isotopes can change, and therefore, if you can keep on calculating the energy difference in terms of the masses, you find out that it varies from 200 to 210 million electron volt energy per fission. This energy is huge energy. It is, once you compare this energy with the energy which is released in a chemical reaction. In a typical chemical reaction, a very large energy, we say, is of the order of 100 electron volts. Of the order of 100 electron volts is a large energy in a chemical reaction. And those chemical reactions are as big as TNT reactions. So we can see here it is compared to one chemical reaction, this one nuclear reaction releases 1,000,000 times more, about hundreds of millions times more energy. So this reaction is equal to hundreds of million chemical reactions. That is why the fission reaction became instant, important and hit reaction. Another property for the chain reaction is that it is a chain reaction. At least 1 neutron in each fission which strikes a U-235 nucleus and initiated a fission, then 1 neutron is emitted and a chain is basically sustained. So if the reaction is to sustain itself, it will be called a critical reaction. For 1 neutron, you get another neutron as a result of the fission reaction. And that neutron is capable of continuing the fission in another nucleus. So the mass required to produce the critical condition is called the critical mass. A critical chain reaction can be achieved at the low concentration of U-235 without any problem. And that makes the whole difference, that such a reaction is really possible with very low concentrations of U-235. If the neutrons from fission are moderated in water to the lower speeds, then the probability of fission with the slow neutrons become very large in U-235 because the probability of reaction depends upon cross-section. The cross-section becomes large when the energy is low. Cross-section is energy dependent. So the cross-section becomes very high for U-235 if the neutron energy is very low. Then this kind of chain can keep on happening. And the energy release and the breaking into the fission fragments and the neutrons going here and there, and then these neutrons causing further fissions will keep on happening. And in an instant, you will see the whole fuel catching fire of this fission. Let's briefly talk about the fission fragments. Fission fragments are really the products that are produced as a result of fission. They are really highly radioactive. They are produced with definitely very large energy of the order of 200 million electron volts given to two fission fragments. So some of them produce neutron after they decay. And these neutrons are called decay or delayed neutrons. The delayed neutrons, as compared to the prompt neutrons, the prompt neutron was that neutron which was instantaneously produced in a fission, along with the fission fragment. And the delayed neutrons are those which are produced after the fission fragments are decaying after a certain amount of time. But they also contribute in the coming chain reactions. So for a mass number A 93 and 141, we can see the following decay chain happens. The krypton 93 is going into the beta, 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 beta decay, and then becoming stable. Xenon, beta decay, beta decay, beta decay, beta decay, beta decay, eventually becoming stable. You can see for all beta decays, few beta decays are of the order of seconds, few are of minutes, then few are of the years. Therefore, this radioactive element will remain radioactive element, eventually will become stable after the largest thing is indicating its overall decay time. So few of the fission fragments are long-lived, few of them are short-lived. Within days, their radioactivity goes up. The 92 protons of the uranium nucleus must be conserved. So fission fragments and the fission products can pair, possibly like krypton 36 with barium 56, rubidium with cesium, strontium with xenon, and so on. So remember that this kind of pairing will happen, and the total number of protons will remain conserved, and the reactions can take place. Therefore, the fission fragments will have their lives. We must remember that after fission, the fission fragments are really the radioactive elements, and they will dictate their half-life will dictate their presence and the associated radioactivity and the lethalness of the elements. If we look at the mass distribution of fission fragments, in fission of U-235, it is much more probable that they will break into unequal fragments. Most of the, if you plot the atomic mass and the fission products chain, which is formed as a result of the thermal fission in U-235 or in plutonium, we see that many pairs can be formed, but majority of them will peak here and will peak here. And the very, very small number will be of the equal size. Of a 120, 120 will be very small number, 126, 126, 120 will be very small number. But the unequal are really there, and the small and the large. The large mass number and the small mass number fission fragments are really formed with the two peaks. So we must keep in view that the mass distribution is of this type, and all the combinations of the fission fragments are possible. Average fission fragment mass is about 118, but very few are formed about 118. Most of the fission fragment masses are peaking around 95 and 137. Most of these fragments are highly unstable, and some of them are extremely dangerous and lethal, such as cesium-137 and strontium-90. They are really very dangerous for human health. Fission is the result of an unstable nucleus, which is formed as a result of the absorption of a slow neutron. And the barrier is broken and converted when the compound nucleus starts oscillation. Fission can also occur in excitation of the state if the energy is greater than the UV energy or appreciable high, or if it is equal to the barrier energy, then spontaneous fission can happen. And the parameters that influence are Z square and A. So fission spontaneous is possible only for elements that are with A number greater than 230 and approximately X more than 45, the order of 45. We have seen here that U-235 and U-238 and plutonium can have the spontaneous fission rates, but with the half-lives of the order of 10 to the power 18 years, 10 to the power 15 years, 10 to the power 10 years. However, for californium, you see it is only 60 years. So for the higher A numbers, for 256, it is in hours. For 260, it is about 7.2 milliseconds. Now let us very briefly talk about the neutrons and their classification, how people term the neutrons according to the energies. There are cold neutrons that are with this almost zero energy or very small energy. Neutrons that are in thermal equilibrium with a very cold surrounding, such as liquid helium, deuterium, they are called cold neutrons. The thermal neutrons are those neutrons that are in thermal equilibrium with surrounding at the 20 degrees centigrade. For the Maxwellian distribution, the value of the energy comes to be 0.025 electron volts. Remember, for Maxwellian distribution, the average energy is equal to 3 by 2 kT. K is the Boltzmann constant and T is the temperature. So if you substitute the temperature value and the Boltzmann constant, you will get the average energy in terms of joules, and you convert the joules into electron volt, you will find 0.025 electron volt energy. This is the energy of the thermal neutrons in thermal reactors. The epithermal neutrons are the neutrons that have the energies larger or better than 0.025 electron volt or 0.04 electron volt, but less than 1 electron. The cadmium neutrons are those neutrons that are at the cadmium cutoff or below cutoff. The cadmium cutoff is the energy of 0.5 electron volts. So all neutrons with the kinetic energy below the cadmium cutoff are the cadmium neutrons. Epicadmium neutrons are those neutrons that have the kinetic energy above the cadmium cutoff energy. So the larger values of energy, 0.5 to the higher energies. The slow neutrons are those neutrons that are really in the range that are not really slowed down to the thermal neutrons, but are slowing down. So of the order of 10 electron volts to 1 electron volt is the range of the slow neutrons. Resonance neutrons are those neutrons that are occurring in 10 electron volts to about 1,000 electron volts. They are the resonance neutrons. You will find the resonances, and we will talk about them in coming slides. They are resonance neutrons due to special behavior of the cross-section. Intermediate neutrons are those neutrons that are in between the very fast range and the epithermal range. It's about 300 electron volts to 1 million electron volt. And the fast neutrons are those neutrons that are between 1 million electron volt to 20 million. They are really produced electrons. They are really fast neutrons that are produced in fission. In fission, of the order of 10 million electron volt energy neutrons are produced, and they are termed as fast neutrons. So this is the range. Relativistic neutrons are those neutrons that are beyond 20 million electron volts. So neutron energy dictates the name of the neutrons. So we say the fast neutron, a very high energy neutron, epithermal neutron, a cadmium cutoff neutron, the thermal neutron, a cold neutron. Let's see the cross section. We have already discussed the cross section is the probability of reaction in terms of the area seen by the incoming particles for the nucleus to do the reaction. So the cross section is shown here in barns. It is 10 to the power minus 24 centimeters square. Area is in 10 to the power minus 24 centimeters square barn. And here we see the logarithmic scale. It is 1, 10, 100, 1000, 10 to the power 4, 10 to the power 5. So it's a logarithmic scale going in a non-linear fashion. On x-axis, it is also a logarithmic scale from 10 to the power minus 10 to 1 million electron volts. So very low energy to very high energy. So if you look at this low energy, it is the thermal energy range. And this very high energy is the fast range. And if you look at the behavior of this fission cross-section, the probability of reaction, then this is 1 over v behavior. The neutron, as the energy increases, the velocity changes, the velocity increases. And 1 over v stands for this fact that the increase of the velocity decreases the cross-section as 1 over v behavior in a straight line fashion. For this, you can see. Then there is a peak, another peak, and so many peaks. This first peak is the first resonance for U-235, and then the second resonance and third resonance, and so many other resonances. And then there is resonances are really smeared and collected together, and they are shaped in the broad resonances form. A resonance is a type in which the cross-section peaks. And in some cases, it peaks more than the 1 over v behavior values. So resonances are where the cross-section peaks or becomes large. So especially in the energy values, the probability of reaction becomes very large. You can see here for U-235, the thermal neutron cross-section is very high. Therefore, probability of reaction is very high. So fission will happen for these neutrons in a very, very high manner. Manifold 10 to the power 4 cross-section as compared to 1. So about 10 to the power 4 times high cross-section can be found if you have the fast energy or comparable neutrons with the thermal energy. If you compare the fast neutrons with the thermal neutrons, the cross-section, the probability of reaction is about 1,000 times higher as compared to the fast energy neutrons, particularly the fission. So fission can happen more easily here and less probably here. Or in the resonance, it is comparable, but for special energies. So if we categorize the cross-section, it has a 1 over v behavior. Then resonances that are split resonances, that are separable resonances. Then there are resonances that are broad resonances, but the energy, the cross-section, as energy is high, the cross-section is low. Let's see the fission cross-section and compare it with U-238. The similar cross-section for U-238 is shown here and compared with the U-235. 1 over v behavior, the resonances, the broad resonances, and here you see this cross-section is going down to very small values. And it is not there, not at all there, which means that this reaction is a threshold reaction. For energies lower than 10 to the power 5, there is no reaction that is going to happen. So fast neutrons, for very fast neutrons, U-238 will fission, but it will not fission for the thermal neutrons. For thermal neutrons, the fission will be about 10 to the power 3 to 10 to the power 4 times large as compared to these So one thing is that they are not showing any fissioning for the thermal neutrons, epithermal neutrons, even for the first initial region. They are threshold reactions. So we call U-238 as a fertile material. It can be made into a fissionable material by absorption of neutron into U-238 and converting it into the plutonium. But U-235 is a fissionable material. So it is a fissionable material, and this is a fertile. So it is a fissile material, a fissionable material, and it is not fissionable material. Let's compare U-235 with the thorium. The thorium-232 is a very special case. You see here again, in comparison, the blue color line is for U-235, red line is for the red line is for the 238, and the thorium is the black line. It is a threshold reaction with a low probability, and the thermal neutrons are not really good. So epithermal neutrons and the fast neutrons are good. Therefore, thorium is not very well suited for the thermal neutrons. Here we stop our today's discussion on fission. We will continue further, and our next topic will be how to control fission and develop the nuclear power reactors, how nuclear reactors were developed, and what are the components and the major parts of the nuclear reactors, in particularly what is the nuclear physics telling us about the nuclear power reactors. Thank you so much.